So far we have seen that how we can reduce a problem with the help of another problem, and it was very helpful, since if my previously proven problem has been proven to be an undecidable problem, and if we could map my new problem with that of the previous problem, we could easily come to the conclusion, okay, this is an undecidable problem as well. We were not proving the new problem again, but just we were mapping with the previous one. Now in today's lecture we will see a technique using which we can just map some instances of one problem to the instances of the other. Okay, and always the mapping cannot be done. Sometimes it will be successful, sometimes it will be unsuccessful, and in case of unsuccessful problems, so we will be sure enough that okay, this problem is not going to get reduced to this problem, so we have to think of the other problems, right? So let us begin. What is post correspondence problem is? Here the formal definition of the post correspondence problem is given. What it is saying that there will be two lists given to us. Why we are saying list? Say we can transform any problem or any languages which Turing machine accepts. That is nothing but all sort of problems which we can generate an algorithm or whatever it is, but for now we will think in the perspective of Turing machine. So we can write any problem using the code for Turing machine technique, so we can represent it in the form of zeros and ones, right? So binary strings. So here two binary strings list will be given. One will for now we will assume one as A and another list as B, right? So A's list say is containing of say 5 sort of strings. Here we are for generalizing purpose we are using K. Right, so it will consist of K strings. Again list B will also consist of K strings, right? And the restriction is such that the number of strings present in A and the number of strings present in B should be equal. That means if my list A has 4 instances, my list B should have 4 instances of it, not lesser, not greater, right? And the input alphabet should be same. That is, for now here we are going to represent everything in form of binary, but say if input alphabet for problem A or list A is 0 1, it should be 0 1 for B as well. Okay, we are not going to use any different set of alphabets for these two lists, otherwise it is not possible to carry on this algorithm. Fine, so what we are going to do here, few instances will be given. Instances means what? Say W1 is consisting of some sort of zeros and one, some sort of binary strings is 1 0 1 1. W2 is consisting of something, W3 is consisting of something. In this fashion there are some instances of the first list. Similarly second list will have some instances which we are considering under the header of X. So we have to arrange the list in such a manner. Here in formally we have to say that we have to arrange the instances or map the instances of the list A with the list B in such a manner so that the output is same. That means say we are generating one instance of the first list as W2 W1 W1 W3, right? That means we will write whatever W2 is having, say 1 0 1 1, then we are repeating W1 twice, we will write it twice, then we will put W3 after that, right? So a total bit of zeros and ones will be generated, and the same fashion, that is x2 x1 1 x3 we have to write, and we have to map, or we have to check whether it is equal or exactly equal with that whatever we have discovered in case of W strings, right? So I'm not telling that the pattern will be always W2 W1 W1 W3. No, it totally depends on the problem which you are working on, and you can use any number of string rather any string any number of times, right? And can follow any pattern. So W3 can come first, W2 can come first, you can use W3 twice, you can use W1 twice or thrice, whatever may be, but it should be same for both W and X, right? The arrangement should be same. Fine. So let us see an example. You can see here, as we have seen in the definition, that there will be two lists, right? List A and list B. See here, I is the counter, and here list A consists of the strings which we are denoting with W suffix I, right? And for list B it is denoted by X suffix I. So for the first one, that is W, first instance is 1, second instance is 10111, and third instance is 10. Since it has 3 instances, list B should have 3 instances as well, so it is having 3 instances. Now we will see an example, or rather we will work on this example only, and you can see that at the end of the day we'll come to the conclusion that okay, this instance, so this set of problems is having a solution. That means after arranging W's in certain fashion and applying that particular fashion to the list B, we can come up with the same sort of strings, means the total binary strings for both the cases will be same. And after ending of this example, we will see another example where we will see that whatever the fashion you try to arrange, you can never come up with a solution. That means that PCP solution is not existing. That means we cannot map list B or the instances of list B to the list A or the reverse. Okay, so let us begin. Okay, so here we are assuming M to be 4. M to be 4 means we will work with, you know, the arrangement where we will the total number of strings used will be 4. Here it is not constant. You can work with anything. You can work with 5, you can work with 10, you can work with 100, whatever it is. But for the sake of simplicity, since just we are learning how to apply this PCP, we are assuming M to be 4, right? Fine. So if M is equals to 4, we are considering I1 to be 2. I1 to be 2 means the first used string from both of list A and list B will be W2 and X2. Okay, why we are doing like this? Whenever you will be given this kind of problem, you have to check for each and everything. Say if you are choosing I1 equals to 1, so in that case you have to start with W1 and X1. Okay, we have chosen this pattern because for this pattern the solution is existing. Okay, so you can try with other patterns, their solution may exist, may not exist. You cannot, we cannot guarantee beforehand, so you have to try it of your own. Fine. So for now we will just consider this pattern where solution will exist, and at home you may try different patterns where solution may exist, may not exist. Fine, but here our focus is to find out at least one solution. That's why we are picking up this one. Fine. So I1, we are considering I1 to be 2, I2 to be 1, I3 to be 1, and I4 to be 1. So the pattern is 2 1 1 3. So how we are going to arrange? For W it will be like W2, then W1, then again W1, then W3, and same for the X or list B, right? So if you just concatenate these two, you can find that the string which we are generating are same for both the cases, right? So if you concatenate W2, W1, W1, W3, and in the same time if you concatenate X2, X1, X1, X3, the output pattern will be same, right? So this is a solution for this particular PCP. What is the solution? 2 1 1 3, right? Again, you see, this is not a unique solution. Another solution can be this one, 2 1 1 3 followed by 2 1 1 3. It is very easy to guess from the given solution, and so one more solution is given, 2 1 1 3 followed by 2 1 1 3 means if you write W2 W1 W1 W3 W2 W1 W1 W3, a certain string will be generated, and apply the same thing for the list B. Fine, so the result will be same. There may be many more solutions. For some choices it will work, some choices it will not work. So for those it is going to be successful, all those will be the solutions. Okay, now let us see one more example where we cannot generate any solution after so many tries. Let us see here. what we are doing here, we can see that there will be no solution exist. Okay, for the, just to start, we will assume I1 to be 2. Okay, we claim that I1 to be 1, but beforehand we will prove that if we start with I1 we can move to certain steps, but we will not come to the solution, fine, but we can move at least. Now for just to begin with the process, we will assume I1 to be 2. That means my string is going to get start with W2 for list A and X2 for list B. Okay, so W2 is what? 0 1 1 and X2 is 1 1. So definitely it is not going to work, because if you start with this, list A is having a 0 before, means list A is starting with 0, whereas list B is starting with 1. So this is a failure attempt, right? So if we proceed in a different way, without assuming I1 to be 2, if we assume I1 to be 3, what will be the case? If I1 is 3, again the same case, just see W3 is 1 0 1, but X3 is what? 0 1 1. So my list A is going to get start with what? 1 0 1, and my list B is going to start with 0, right? And so this is not possible. So rather, if you just follow the chart, you can see where the same pattern, means at least for the beginning we have to start with something which is having the same starting string, means the same starting input value is same. So it is definitely I1, right? So if I1 is 1 0, if I1 is 1, rather W1 is 1 0 and X1 is 1 0 1. So at least the starting strings are matching, right? So then we have to concatenate something which can come to this conclusion that okay, a solution may be there. Okay, so here if I1 equals to 1, that means W1 is 1, so it is starting with 1, and for X1 it is again starting with 1. So let us move on. Okay, so I1 we have assumed to be 1, fine. Now the case of I2, means the second value. If we are assuming second value again to be 1, so what is it? It will be W1 for list A and X1 for list B. Okay, so if you see, if I1 is 1 and again I2 is also 1, so the concatenated string will be W1 W1 for list A and X1 X1 for list B. So just see, it is not matching at the fourth location, right? So fourth location of the first list is 0, whereas the fourth location of the second list is 1. So we have to discard I2 as 1. Fine, let us try for I2 equals to 2. If I2 equals to 2, then my concatenated string will be like W1 W2 for list A and X1 X2 for list B. Fine. So here if we concatenate W1 with W2, it will be somewhat like 1 0 0 1 1, right? But for this list it will be 1 0 1 1 1. Just see, it is again mismatching at the third location, right? So it is not working. So if we consider I2 as 3, then let us see, if I2 is 3, then what will be the pattern like? If I2 is 3, it is like W1 then W3, so it will be 1 0 1 0 1 for the first list, and for the second it is 1 0 1 0 1 1. Now see, it is matching, still now it is matching. B's length is 1 larger than that of A, fine, but if you keep up to this, again you cannot say that both A and B, whatever the list is generating, are same, because one is lacking in the list 1, right? So again both are still, now it is matching up to 5th location, fine, but 6th location does not exist for list A. But you cannot extend the list anymore. You can try any pattern for I3, right? We have done up to I2, but if you try on with any one values for I3, right? So you cannot come up with a conclusion, means right? So here you can see that one extra 1 is there for list B. So what we have to means to come up to a solution, what we have to do, we have to incorporate one in the list of A. So the choices are what? I3 can be 3, right? Why 3? Because list A is having a starting value 1 with that of I3, right? Third value. So fine. So if you just try with this pattern, I3 equals to 3 and I4 equals to 3. So if you can come up with a conclusion that okay, both the lists are generating the same input pattern, it is not mismatching at any position, then that it will have a solution. But just try it of your own with these two values, that is I3 equals to 3 and I4 equals to 3, or any other length strings. Here we are just focusing on m equals to 4, but you can increase the length as well. But you cannot come up with any solution. So you can see that for this particular problem no solution is existing, but in the previous problem we have seen a solution exists. So this is how we can map one problem instances with the problem instances of the other problem, right? Thank you. And with this we are going to end up the module 3 part, that is the Turing machine part, and then from the next class we are going to start with the module 4 of our syllabus. Thank you.